Alright, so today we're going to look at how to write the noble gas notation and orbital notation. Noble gas notation is our shortcut to writing electron configurations. So, first of all, I just want us to write the electron configurations for sulfur, potassium, and iodine. Just the regular ones we learned yesterday. So you work on those, and I'm going to write them. And you can check your answer and make sure you understood yesterday's video. Alright, so as you can see, they get progressively longer the further down the periodic table we get, and so they're going to become much, much longer. Right, so how do we write this noble gas notation? Well, we use our noble gases, and our noble gases are in the very last column over here. Right, and they're called our noble gases, or also known as inert gases, because they have full energy levels, so they do not react with other things. And so what we do is we look at the noble gas which came before it. So we find our preceding noble gas. Right? And so for sulfur, that would be neon. And if you remember, neon's configuration ends in 2p6. So it has 1s2, 2s2, 2p6. And so what we do is we replace those electrons with just writing neon in brackets, which would mean we have all these same electrons as as neon in sulfur, and then we also have 3s2, 3p4. Alright, so let's apply that to potassium. So potassium is here. Its preceding noble gas is argon, which would end in 3p6. So let's find 3p6 in the electron configuration. It's right there. So we're going to place all of those electrons with argon, and then just write 4s2, because that's what's left to get to potassium. See how much shorter that makes that? So much easier. So same with iodine. So go to the preceding noble gas, which is krypton. That would be 4p6. So again, in our electron configuration here, we find 4p6. We're going to place all those electrons with krypton, and then the ones that remain get us to iodine. That's a 4, and then 5p5. So that's noble gas notation. Shortens it up a lot. Alright. Next, in orbital notation, we further break down the location of our electrons into what orbital they're located in. Okay, so each of the sublevels, S, P, D, and F, have a certain number of orbitals. Well, the S sublevel has 1 orbital, the P has 3, the D has 5, and F has 7. It's easy to remember those, 1, 3, 5, 7, because they're the odd numbers in order of increasing energy. Remember yesterday we talked about how S has the least energy and F has the most. Now the maximum number of electrons that can be present in an orbital is 2. So since the S sublevel has 1 orbital, there will be 2 electrons maximum. P's have 3 orbitals, so that's a maximum of 6 electrons, 10 and 14. And we showed that yesterday when we were looking at electron configurations. For orbital notation, there are 3 rules that we must abide by. The first we already talked about, I just didn't call it that. That's the off-ball principle, and that says we must begin electron configuration with the least energy orbitals possible. With the least energy orbital. And that's going to be your 1s. Right? So that means you have to fill them in order of energy. And that energy is in order on the periodic table we discussed. 1s, 2s, 2p, 3s, 3p, 4s, 3d, 4p. That is in order of increasing energy. Okay? Pauli exclusion principle says that no two electrons can have the same set of quantum numbers. And so what that really means is that they must be different. So no two electrons can be exactly the same. And how that corresponds to us here is that if we have two electrons in one orbital, they must have opposite spin. Okay, and we show that spin by doing arrow up and arrow down. That shows us that spin. Okay. Hund's rule tells us that we must occupy each orbital in a sublevel before doubling. An example of that would be a p sublevel. Let's say this one. Let's say we wanted to put 4 electrons in that p sublevel. Hund's rule says we have to do 1 electron in each orbital, and then we can double. It also says occupy each orbital in a sublevel before doubling, and all those electrons must have the same spin, which is why I did them all up first. Okay? So we're going to use those rules to write orbital notation. Alright, so next, let's look at cobalt. Let's find cobalt on our periodic table. It is right here. Okay? I personally like to write out the electron configuration first. So it would be 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d, 1, 2, 3, 4, 5, 6, 7. Okay? So now, if we go back to looking at our notes, we know that we have a 1s, so that has one orbital. We're going to label it 1s. We have a 2s, that has one orbital. Label it 2s. And then we have a 2p, and p's have 3 orbitals, so we draw 3 lines. 1, 2, 3. We'll label that 2p. Then we have a 3s, so that's one orbital. Label it 3s. 3p, we have 3 lines for that. We're going to label that 3p. Then we have a 4s, which is one orbital. And then we have a 3d, which is 5 orbitals. 5. And we call that 3d. Right? So then remember, our superscripts are our number of electrons. So we put electrons in using arrows. Arrows represent our electrons. If we have 2, one has to be spin up and one has to be spin down. That's Pauli exclusion's principle. Likewise with the 2s, one up and one down. 2p has 6, so each one would have one up and one down. Then we have 3s, and then we have our 3p. They're all filled in, and then our 4s. But then we come to our 3d, which is not completely full. So according to Hund's rule, we have to put 1 electron with the same spin in each orbital, and that's 5, and then we can come back and double 6 and 7. Okay? In this case, we would have 1, 2, 3 electrons which are unpaired. That's going to be important for a lab we're going to do, but there are 3 unpaired electrons. meaning there are 3 electrons which are in an orbital all by themselves. Alright, so I want you to try sulfur and have that ready for class tomorrow.